I'm Panita.
Hello, I'm Daniel. Punita, I would like you to imagine that behind us there are two big water tanks and they are connected by a channel that allows water to flow through them.
All right. Is there a particular reason I'm thinking of two water tanks?
It's to demonstrate the flow of electricity and to help you better understand electric current and voltage, what we've been talking about.
All right. Two water tanks.
You got it in your head? Mm-hmm. Now, what would happen if I poured water into one of the tanks?
I guess the water will flow through the channel connecting them until the water level of both the tanks are equal and the same. It's not that difficult to understand.
Electricity flows exactly the same way. But just like the water level in the water tanks affects how it flows, we say electric potential for the electricity.
Oh, okay. Electric potential.
And as you just said, just like the water flowing from a high pressure area to a lower pressure area, electricity flows in a similar fashion. The electrical current flows from a higher electric potential to a lower electric potential according to the difference in electric potential.
Okay, it's kind of a difficult concept to understand, the difference in electric potential. So if we don't know this, does it mean we can't do the maintenance work?
Well, when we express the electric potential difference as a number, we use a shorter term called electric pressure, or more commonly known as voltage. And if the electric potential is relatively high, we call that a positive pole. But if it's low, we call it a negative pole.
Okay,
very good.
Got it. Positive and negative. It's a little more familiar, like we see on the batteries.
In a battery, the electric potential difference will be zero when the electric potentials of both poles become equal. That means the battery is empty. To recharge the battery, we need to increase the electric potential of one side. It's like redirecting the flow of the water so that one tank is full and the other one's empty.
Yeah, somehow, if you give me the context of batteries, it's easier than I thought. But what about the electric current we're talking about? Does this have anything to do with the use of high voltage in EVs?
Wow, very good question. You're getting ahead though. Let's take it one by one. Okay, so let me explain electric current first, and then after that, you'll see why high voltage is a must for EVs. As I told you, the electric pressure or voltage, it's like the difference in water pressure between the two sides of the two tanks. Just as the higher water pressure enables a greater flow of water, a wider pipe will also increase the water flow. Right? So think of electric current or amperes as the area of the cross section of the pipe between the two tanks.
Okay, so if you want to increase the electric power, you can either increase the electric pressure, the volt, or the electric current, which is the ampere.
That is correct. But there is a reason why we prefer high voltage rather than a high ampere when it comes to EVs. Remember, I just told you that the amperes is like the cross section of the pipe connecting our two water tanks, right?
Right.
Similarly, what must happen in order to increase the electric current or amperes?
We need to thicken the cable.
Very good.
Yes.
You're absolutely right. See, yeah, you're getting it. Increasing the thickness of the cables in EVs means a heavier load in the vehicle. Not only it's going to take up a lot more space in the vehicle, it's going to take up a lot more weight. And when we're designing EVs, we don't want to take up space or weight if we can help it. Therefore, we use a high voltage instead of a high current.
I see. So that's why we use the high voltage.
Yes.
Interesting.
Very.
All right, so HEVs, FCEVs, and EVs, they all use this high voltage. But I want to know if there are any key differences between them.
Actually, in some ways, they all have similar systems. The battery delivers electricity to the motor to turn the wheels. Here are some diagrams.
Okay, so this car uses both a battery and an engine, which is an HEV. And there is an EV which moves with only a battery and a motor.
Bing, bing.
And there is an FCEV which uses a fuel cell instead of a battery.
Bing, bing, bing.
There you go. I thought these EVs were complex, but these diagrams, they make it look a lot simpler.
That is correct. None of it's really all that difficult. Of
Sure.
course, there are many complex devices in EVs, and they are located in different places throughout the car, depending on what vehicle you're talking about. But to put it simply, these are the flows of electricity.
All right, so these are the inner workings of them.
Let's look at them one by one, shall we?
Great.
Okay, so according to our diagram here, what is the battery connected to?
The battery is connected to inverters.
Very good.
Inverters connect the DC from the battery into the three-phased AC. It's a lot easier to comprehend, but now what about the LDC?
An LDC, that stands for low voltage DC-DC converter. Electric vehicles also use 12 volts to do general electric operations. I'm talking things like turning on the headlights or using the windshield wipers. So here is the LDC, it's right under here. The LDC is a converter, and it converts the high voltage of the battery to a lower voltage.
Well, I thought EVs operated entirely with high voltage. Then do you really need to use the 12 volts?
If the electric components used in an internal combustion engine vehicle can be used as is, that's definitely an advantage. So the computer that monitors the condition of the battery also powered by a 12-volt battery.
Oh, I see.
Okay? And also, for an extra layer of safety, can never have too much safety, we need a separate 12-volt battery.
A battery for safety.
Yeah. By design, the high voltage battery, the real strong one, that shuts off when the car is not being used. When you press the starter button in the car performs a safety check. And only if everything is perfectly normal, the battery gets connected to operate the vehicle. So the 12-volt battery acts as an essential standby unit before the high voltage battery gets connected.
I guess I can see why you do need an LDC right here, right?
Right, underneath.
Okay.
Let's take a look at this. That's the OBC. OBC stands for on-board charger. Those are only used in PHEVs and regular EVs.
So the charger is mounted inside the car. Is that necessary?
It is for charging compatibility. As I mentioned earlier, the motor uses a three-phase AC, but the battery needs DC. Remember? So DC is necessary to charge our high voltage battery. However, electricity for households and industrial use is all AC, right? Stuff coming out of the wall. So for normal AC charging, a 100 to 220 volt AC from an external source gets used. That AC gets converted to DC, then boosted to a high voltage to charge our high voltage battery. That role is performed, bam, by the OBC.
The OBC, big boy OBC.
Yeah, you got it.
But now these HEVs use both engine and battery power.
Very good.
So both an engine and fuel tank are needed, but as charging isn't necessary, HEVs don't have an OBC. PHEVs, on the other hand, they do need charging, so they have an OBC to take care of that, right?
Very good. They have more characteristics of EVs than HEVs. PHEVs, they're designed to run exclusively on an electric motor for a long range, and that's compared to HEV. That means the PHEVs require a stronger output from the electric motor, and so bigger batteries. That allows them to drive only with that electric motor for dozens of kilometers.
So then I suppose that PHEVs require higher voltage than HEVs.
Correct. Also, EVs use higher voltage than PHEVs. The Ioniq 5 is mounted with an 800 volt system. And among the many types of eco-friendly automobiles, EVs, they have the system with the highest voltage.
Well, didn't you say that the Ionic 5 doesn't have an OBC?
No, that's not right. Even the Ionic 5, which uses the eGMP, still has an OBC. It needs the OBC, if you remember, to convert the AC into DC.
That's right, yeah.
However, starting with the Ionic 5, the OBC, that's been integrated into the Integrated Charging Control Unit, what we call ICCU for short. So, to summarize, AC from charging is converted into DC by the OBC inside the ICCU.
All right, I think I got it.
Good.
You know, I also noticed orange cables in these eco-friendly cars. It's really pretty. What are they?
Okay, well, you already know that various kinds of electricity are flowing through an eco-friendly vehicle. Among these, you see an orange cable. That indicates high voltage current.
So making it visible with the orange color is to emphasize the need for caution.
Correct. Orange means watch out. As I said earlier, in general circumstances, there should never be a problem. But some of the people watching this video, they may face certain situations. For example, having problems with a car or with a repair. Through accidental contact with the high voltage cable, a person can suffer electric shock, and it can be very, very dangerous.
Oh my gosh, I don't want to imagine that.
So, to avoid these kinds of events, we have the high voltage cables. They are wound with multiple layers of insulators, and the cable itself has a safety circuit. So what that means is if a cable is removed from a socket, open or short-circuited, the power, it's shut off automatically.
Oh, that's great. What a relief.
Yeah, well, it's very important for safety. In fact, so important, I'm going to explain in greater detail. When the high voltage connector gets pulled out, what happens is the interlock circuit, it senses that, and it shuts off the high voltage immediately. When the cable gets opened or it's short-circuited, the current that's flowing through the high voltage system as a result of that will decrease unusually. The system will detect that and shut off the high voltage.
Wow.
Or if the current rises above a normal level, that will cause a fuse to blow, shut off the high voltage current.
There's a lot of technology in these high voltage cables. You always want to be safe.
Yeah, and that's why we have all those systems. And it's also why when technicians need to come into contact with high voltage wires for any kind of repair, they have to follow all safety regulations and wear PPE. And in the next session, we'll talk a little bit more about those.